Hi everyone, my name is Jiasheng from the Small Artifacts Lab at the University of Maryland. I'm excited to present our work comparing vibrotactile and skin stretch haptic feedback for conveying spatial information of virtual objects to blind VR users. This work is in collaboration with Zining Zhang, Zeyu, Yuhang Zhao, and my advisor Huaishu Peng. Spatial information is essential for users to perceive and navigate a 3D virtual environment. For sighted users, spatial information such as virtual objects' positions and moving directions are delivered primarily through visual simulations on head-mount displays. However, this vision-centric approach poses significant barriers to blind users, preventing them from perceiving and understanding spatial information in a VR space. Peer's work for making VR accessible, such as assistive auditory system, has provided blind users with spatial information. However, the audio-only feedback can be easily interfered from various sound sources, such as ambient noise, background music, or speech from other avatars sharing the same virtual space. As a result, relying exclusively on auditory feedback is frequently inadequate for delivering clear and reliable spatial information. Beyond spatial audio, haptics as an independent sensory channel has been used and researched to convey spatial information. For example, tactile gloves equipped with vibration motors to navigate users in 3D spaces. Gaiters is a leg-wear device aims to provide force and stretch feedback. However, these devices primarily aim to enhance VR immersiveness rather than provide spatial information. More importantly, they have not been evaluated with the blind and low vision community. Here, we have a question. How can we render the spatial information of a virtual object to blind users in 3D spaces through haptic feedback? To answer these questions, we conducted an empirical study with 10 blind participants. We investigated and compared two haptic mechanisms, vibrotactile and skin stretch, for conveying both static and dynamic spatial information of virtual objects on the dorsal side of user's hand. We choose this combination of haptic feedback mechanisms and body location for three prime design considerations. First, Peer's researcher has showed that the skin on the hand has relatively high sensitivity compared to many other body locations, making it potentially effective for rendering spatial information. Second, compared to other parts of the hand, the dorsal side offers sufficient flat area that is not involved in VR operations when blind people interact with VR controllers. Third, both vibration and skin stretch mechanisms can be engineered with small factors and low cost, critical consideration when designing assistive technology. In our study, we recruited 10 blind participants through our local mailing list of the National Federation of the Blind organization. Among all participants, 3 participants mentioned they have minimal VR experience, which was limited to wearing a head-mount display or hear audio from the menu screen without fully understanding the virtual environment. All participants were familiar with vibrotactile feedback, and their dominant hand is the right hand. In our study, we designed a 3-axis gantry experimental device. As shown in the left figure, the 3-axis gantry system is equipped with a camera to calibrate with different size of user's hand, a hand rest for users to put their hands on, and a multifunctional touch probe capable of rendering both skin stretch and vibrotactile feedback. To render skin stretch feedback, the touch probe lower along with the Z-axis until it makes clear contact with the user's skin, and then probe move toward to the direction. To render vibrotactile feedback, the touch probe first lower at the center of the hand dorsal and vibrate, then lift up, move to the target point, and lower down again and vibrate upon contact. To map the location of a virtual object relative to the user's position, we designed a coordinate system on the dorsal side of the hand. We divided the surface of the dorsal side of the hand into 8 directions, and we added 2 haptic points along each direction to represent the varying distance. In the task 1, we investigated how blind individuals perceive static spatial information, for example, direction and the distance of a virtual object, through skin stretch and vibrotactile haptic feedback. We collected 960 trials in total, including 48 trials for each participant. In completing each type of haptic feedback, we evaluate participants' perception by calculating their accuracy in reporting the directional and the distance information. The scoring system used 1 point for a full score, half points for a partial score, and 0 for no score. After completing task 1, we conducted a semi-structured interview and collected the answers for questionnaire to compare 2 types of the haptic feedback. Task 1 result, we calculated the mean score from 960 trials across 2 haptic feedbacks on each point, with higher scores indicate higher accuracy. Overall, we find significant effect on haptic mechanisms on participant accuracy in perceiving spatial information. We found the blind participants showed higher accuracy with skin stretch feedback compared to the vibration feedback. We also examined the directional and the distance perception. Scores for each direction were calculated based on the correct directional or distance responses. We see skin stretch feedback outperformed better than the vibration on all 8 directions, and also for near and far distance. After completing task 1, we also asked participants to complete the NASA TLX questionnaire to access the task load. We didn't find a significant effect of haptic feedback mechanisms on participant understanding of distance or directional information or on their confidence. In the task 2, we investigated how blind participants perceive the spatial information of a moving object. Specifically, we introduced 10 test paths, categorized into 3 types. First, a single direction moving objects. Second, multiple direction polygon trajectories, and curved and S-shaped trajectories. Similar to task 1, we found significant effect on haptic mechanisms on participants' accuracy in perceiving moving object spatial information. We find blind participants showed higher accuracy with skin stretch feedback compared to the vibration feedback. For more detailed information, please refer to our paper. In conclusion, which haptic mechanism is better? Our study demonstrates that rendering haptics on the dorsal side of the user hand can indeed help blind users perceive both static and dynamic spatial information, and the skin stretch has higher accuracy than vibration. We also find divided preference among the participants. Several participants favored the vibration cues, cited greater familiarity with vibration based on the feedback in their daily experience. Other participants state that the skin stretch haptic feedback is more practical and useful for them. Nevertheless, we recognize the benefits of both haptic mechanisms for rendering spatial information, as some participants suggested it should be feasible to combine them. Future research should explore the potential of such a combination. Thank you for listening.